Assalamu alaikum. My name is Shakil, and today I'm going to be covering Chapter 8 of Physics 11, which is about waves. So, today I'm going to be covering several different topics. Firstly, I'm going to ask, what is a vibration? What is a wave? What are the parts of a wave? What are the characteristics of a wave? What are the types of waves? How do they behave in terms of the particles in regards to the media that they're in? Wave speed and the associated formula, and then lastly, I'm going to talk about sound. According to the textbook, a vibration is a cyclical motion of an object about an equilibrium point. Before we dive right in, let's take a step back and see what this means in depth. Firstly, an equilibrium point is the point halfway from the minimum or maximum distance. This is better explained with an example. Say you have a pendulum that is swinging back and forth. It may swing all the way this way or all the way there, but the point in between the center is the equilibrium, so that black point over there. Secondly, a cyclical motion is simply a motion that occurs in cycles. For example, the pendulum swinging back and forth. Okay, so next, I'm going to talk about the main bulk of the chapter, which is about waves. So, quick recap, I'm going over what it is, parts of it, types of waves, and how particles behave in regard to waves. Note that we will be talking about mechanical waves. So firstly, what is a wave? So, according to the textbook, a mechanical wave is a transfer of energy by particle vibration that is caused by a disturbance in the medium through which it travels. In layman terms, an external force causes a vibration, which then transfers the energy and the vibration throughout the medium. There are many parts of a wave. The diagram here is a transverse wave, but often longitudinal waves are stretched to make them easier to read and measure. I'll explain a bit more about these types of waves and how they differentiate in a moment, so that should make a bit more sense. The first part of a wave is amplitude. This is the maximum distance from the equilibrium. Above the equilibrium, it is called a crest, and below it, a trough. Here, the equilibrium is the center line. The wavelength, represented by the Greek symbol lambda, is the distance between two similar points on successive cycles of a wave. So, for example, the distance from the crest of one wave to the next is called a wavelength. The unit for wavelengths are meters. A phase is the x-coordinate of any unique point on a wave. So, for example, if there's a point on the wave with a x-coordinate of 0.5, that would be its phase. A phase shift is an identical wave that is shifted along the axis. So, imagine you had another line right beside the line, just a little bit over on the x-axis. Now, before we continue, let's talk about wave types. There are two different types of waves, and they are differentiated by the way they transfer energy. First, there are longitudinal waves, where the particles vibrate parallel to the flow of energy. For example, think of a slinky, where when you throw it, there's a pulse that flows along its length. There are two parts of a longitudinal wave. The first is compression, where particles are closer together, and the second is rarefaction, where the particles are farther apart. Another famous example of a longitudinal wave is sound, which is energy produced by rapidly vibrating objects that we can then detect and interpret. The second wave type is the transverse wave, where the energy flows perpendicular to the flow of energy. An example of this is a guitar string. Particles that are in waves also behave differently based on the medium in which they travel in. In a solid, the particles will always return to their original positions and are thus called elastic. Elasticity is the property of a medium that says that it returns to its original shape after being disturbed. Because of this, and because they are more rigid, solid media generally transfer energy more efficiently. In liquids, sound is better transmitted than air, but less so than solid media. Gases are the least effective at transferring energy, and they rely upon straight-line motion of molecules to do so. Now, there are several characteristics of waves. First is frequency, which is measured in hertz, or Hz. This is simply the number of cycles that complete in the allotted amount of time. So, if the time period is usually 1 second. So, if a wave completes 5 cycles in 1 second, it has a frequency of 5 hertz. A period, on the other hand, is represented by the letter t, and is the time for a vibrating particle to complete 1 cycle. In comparing the two, we can see that frequency is how many cycles that occur in the time given, while a period is how long it takes for 1 cycle to complete. We can show this relationship with f equals 1 over t, and we can algebraically rearrange this to the format t equals 1 over f. With this, we can find wave speed, represented by the lowercase v. It represents the speed by which a wave is traveling through a medium, and by extension how fast the energy in the wave is moving. It's measured in meters per second. Speed is simply distance over time, and in this case the distance would be the wavelength, and the time would be the period, which is the time for one cycle. So v, or speed, is equal to lambda over t, meaning the length of one cycle over the time for one cycle. A common type of vibration is simple harmonic motion, where motion repeats itself at regular intervals about an equilibrium. In this case, the amplitude, frequency, and the period is the same for each oscillation, or vibration. Wave speed is also calculated with the universal wave equation, which is v equals frequency times lambda. So now let's solve an example. This is sample 2 on page 389. The question here says, a trumpet produces a sound wave that is observed to be traveling at 350 meters per second, with a frequency of 1046.5 Hz. Calculate the wavelength. So we can simply rearrange this algebraically and find lambda. Here, lambda would be speed, or v, divided by f, or frequency, which is 350 divided by 1046.5. Hence, we can see that the wavelength is 0.33 meters. Wave speed is affected by various factors. These include temperature, where warmer means more effective, linear density, and tension. These are in a string. The linear density is the mass per unit of distance of a string, and is represented by the symbol of the Greek letter rho. It is calculated by dividing the mass of the string, which is in kilograms, by the length of the string, in meters. So rho, or linear density, is equal to mass over length. The equation for wave speed along a string is wave speed is equal to the root of the force of tension divided by the linear density, where Ft is the force of tension and it's divided by linear density. Now we will talk about sound. There are three types of sound: infrasonic, audible, and ultrasonic. Infrasonic sound is a sound wave with a frequency below 20 Hz. Audible is sound between 20 Hz and 20,000 Hz, or 20 kHz. And ultrasonic are sound with a frequency above 20 kHz. Ultrasonics are used to safely observe a baby in the womb, break up kidney stones, units in cameras such as those found in the iPhone X, XR, and XS depth perception cameras, and making less detailed X-rays. Sound is calculated by the equation v, or speed, is equal to 331.4 meters per second plus 0.606 times the temperature, which is in Celsius. Remember that this makes sense because speed is actually affected by the temperature. The Mach number of an object is the ratio of its airspeed to the local speed of sound, which again varies based on temperature. This ratio doesn't have any units. So m equals airspeed of object versus local speed divided by local speed of sound. Sound intensity is the amount of sound energy being transferred per unit area, watts per square meter. The pressure of sound is the force per unit area, so P equals F over A, where F is force and A equals unit area. Because watts per square meter is too large of a measure for sound intensity, we use decibels. 1 decibel is equal to 0.000000000001 watts per meter squared, and 100 decibels is equal to 0.01 watts per meter squared. As a sound wave travels through the area increases, and hence the further you are, the quieter the sound is, because the area has increased. Loud noises can damage hearing depending on how loud they are and how long you listen for, and how far you are, of course. But that about wraps up Chapter 8. Thank you for your attention, and thank you for your time.